Hi everyone, my name is Li Mingdong. It's really glad to present my talk at FSE 2022. Semi-supervised pre-processing for learning-based traceability framework on real-world software projects. It's an honor for me to speak on behalf of all co-authors from Software Process Group in Nanjing University DevOps Plus Research Laboratory. Our group's research focuses on software process modeling, software process mining, software process improvement, and process quality measurement. You can find out more about our lab by visiting our website. My presentation will be introduced following about 5 aspects. First, let's look at the study's background and goal. A wide range of industries rely on traceability, including manufacturing, food industry, aerospace, healthcare, and transportation. In these rich industries, traceability is not a choice, but a necessary since they have heavily governed and audited. In the current world of enterprises in software engineering, traceability is a holy grail chased by many organizations. Traceability means ensuring integrity and completeness of the entire software development process. Ideally, the software system should be able to trace different source and target artifacts, such as requirement to design, document, test cases, source codes. Software traceability can also support software maintenance and evolution activities like change management, software reviews, software defect prediction, and so on. My research is about software process, and specifically software process mining and simulation. A process simulation model focuses on particular software development, maintenance, evolution process, which is an abstraction of a real or conceptual complex system. A software process simulation model is composed of process variables and a process flow. To control the process flow, we must measure the process variables and the relationships between each other. Simulation models measure process variables based on realistic history data and monitor dynamic feedback of processes. Therefore, we need actual process data and make sure its quality to satisfy the demands of software process simulation modeling for measuring process variables such as completeness, validity, consistency, traceability. The question is, what is the quality of software process data in the real world? However, the data quality problems caused by the complexity of different software projects across teams, data sources, versions in enterprises still could not meet the demands of software process simulation modeling, resulting in lack of traceability, inconsistency, lack of validity between these process artifacts. Among them, traceability is one of the most significant process-oriented data quality problems. Specifically, issues with human text trace links in real-world projects, including delayed, incorrect, incomplete trace links. Even the worst situation is there is no trace links. As a result of these circumstances, it is difficult to obtain accurate information about each artifact's status stage. The creation and maintenance of traceability are high-cost, time-consuming, and labor-intensive process. It's not advisable to force software engineers to guarantee all forms of trace links. For this reason, we aim to look for automatic solutions for recovering process data traceability. Generally, our study aimed to establish the foundation for data governance for quantitative software process simulation modeling by using intelligent methods to connect different software repositories, artifacts, enhance traceability accuracy, and improve the quality of software process data. Researchers are increasingly exploring and applying traceability techniques. We can observe the evolution of traceability techniques through a systematic review, where most previous studies have invested a lot of efforts in automatic or intelligent techniques, including IR-based, heuristic-based, machine learning-based, and deep learning-based approaches. It is worth noting that Michel's paper published at 2018 on FSE by using supervised learning for trace link classification is an excellent reference. They observed that on average only 60% of commits were related to specific issues, and around 40% of improvements and bugs did not submit along with the commit. This is believed to be the most prevalent state of traceability. As part of Michel's efforts to generate missing link at the commit level, at least per commit with one link, they combine process and text-related features, for example, stakeholders, temporal relations, text similarities between source and target artifacts. To create candidate trace links pairs between commits to issue, they using the matching function and to match each issue with candidate commits that were submitted during its lifetime. However, they still considered a time window threshold epsilon, as well as commit submissions related to the past resolved issues. Michel's work provided a good foundation, and we aim to continue to explore the challenges of Michel's model with more realistic enterprise data. In this study, we investigated a motivating question: how does current machine learning-based TraceLinks classifiers work in real-life projects? Based on 6 OSS projects collected by Michel and 10 industrial projects selected from our collaborators, we experimented with the effect of these models. Observing the bar charts, the industrial projects performed badly, averaging about 30%, as shown in F2 score distribution. This is significantly lower than the performance in previous 6 OSS projects, with close to 80% F2 scores. As a further analysis of the problems encountered by industrial project, we displayed the imbalance radio by dividing the number of false links with true links. The left table shows OSS projects that have maintained comparable size issues and commits for more than 10 years history. However, for most of industrial projects, on the other hand, only have hundreds of issues, but with 10,000 or even 10,000 of code commits created in their short histories. As commits are submitted more frequently in industrial environments, a great proportion of code commits are considered as candidate targets for issues. However, really few commits are actually associated with issues. Another challenge is diversity. We analyze from the aspect of symbol size and the feature space sparsity. For example, in industrial projects, only over 30% of issues have code commits links. Moreover, due to the low quality of recorded data in repositories, many key fields did not fill out, such as issue resolution time and assigned developer. This causes the returns of more sparse process features in industrial projects. Therefore, textual similarity appears to be the most influential feature in both datasets from the upper table. Thus, due to the above issue, we proposed a framework based on a semi-supervised algorithm to address the data imbalance and disparity problems. We call it Splint framework. In Splint, we used semi-supervised learning mechanism during the data rebalancing step. The algorithm can be used to augment sparse labeled data with unlabeled sample. Based on the initial classifier, Pascal labels are assigned to unlabeled samples. However, the traditional semi-supervised learning algorithm did not work well in scenarios with heavier imbalance distribution. To increase and rebalance the labeled training set, a strategy for selecting minor classes over major classes needs to be developed. We used class balance training selection strategy, which would determine the threshold probability independently by selecting the top-ranked p% separately from each class. Due to the number of major classes instances much more than the minor classes, so the overall imbalance radio returns from class balance subtraining is still higher. So we use the sampling rate introduced by Wei-Chen and combined it with class balance subtraining, and which could select 100% from minor classes and select a lower proportion of unlabeled symbols from major classes by controlling sampling rate. As a follow-up to Michel's work, the first step of Splint is to select software artifacts and labels the data and divide them into labeled and unlabeled sets. Then, as a third step, we add more hybrid similarity features, as due to the importance of semantic information in elevating heavier feature sparsity. In the first step, the labeled data was split by temporal orders. As a part of fifth step, the semi-supervised learning mechanism used the class balance subtraining strategy used in the data rebalancing step, which is a core component of Splint framework. We then applied a data oversampling algorithm since we have fewer minor classes. The following research questions are investigated in our experiments. Can Splint better support automatic TraceLink prediction tasks in real-world projects? How is each component enhanced in Splint contributing to effectiveness? How does different parameters in class balance subtraining strategies impact the effectiveness of Splint? Based on the result presented in the upper table, Splint performed better than the classic IR models and the state-of-the-art machine learning models proposed by Michel. Over the 10 industrial projects, the F2 score was higher with 14% and an improvement with over 8% on AUC based on the baseline TraceLink class. In the bar chart, both hybrid textual similarity features and the semi-supervised learning mechanism contribute to its overall effectiveness. Especially the semi-supervised learning mechanism is particularly useful for industrial projects that face heavier challenges related to data imbalance and sparsity. The CBSD adjust algorithm determines the selection threshold value based on the parameters such as top ranked percent, increase rate for each iteration, sampling rate alpha, iteration number. Depending on the simple parameters, the algorithm is sensitive to the changes of those parameters. According to the figure below, it was still difficult to avoid low-quality reliability samples within selection strategies in the tail iteration rounds, as in trans distributions. So here is the summary of our talk. As part of this talk, we discussed the importance of traceability, which can facilitate the construction of simulation model that resemble real-world software process data, and it is an essential part of software data quality. Because of the tight development cycle, for example, 1 month release cycle, software enterprises struggle with weak traceability management. Also, we found that lack of research on exploring practical reasons for underperformance of automatic traceability technique in real-world settings. We observed in a real-world scenario, widely used automatic TraceLink classifier failed to perform well. The problem, such as data imbalance, especially are major challenges in industrial projects. In this paper, we introduced Splint, a learning-based semi-supervised framework, which could mitigate data imbalance and sparsity at the same time. And in 6 open source and 10 industrial projects, Splint has been shown to be more effective and practical for supporting TraceLink's prediction. However, there remains a great deal of work to be done in the future. Further research is needed on Splint's potential for recovering TraceLinks on other types of artifacts. Also, in industrial project, we observed Splint hasn't been able to deliver satisfactory results. This is because the large part of the existing links, that means ground truths, include incorrect tagged trace links due to the human error. So the accuracy of tagged trace links and the robustness of Splint would therefore should be improved in the future work. I really appreciate your watching, and if you have any questions or have interest in our work, please feel free to contact us. Thanks for watching.